let us try to understand some traditional methods used to achieve low temperatures. The first and the oldest method in this regard is the use of salts or the method of freezing mixtures. In this method, ice which is already at 0 degree or below 0 degree temperature can be cooled further by adding salt to it. Instead of salts, some acids can also be used. Of course, these have to be edible in most of the cases. If the mixture is supposed to be eaten, or either they need to be safe because they are to be used with food products. Now, whenever we consider ice, actually small amount of water molecules are always present on its surface, and when we add some salt to it, the salt gets dissolved with this water or in this water. The amount of heat required for this process, called as the heat of solution, and in addition to that, the amount of heat required to melt this ice into water, which is called as latent heat of fusion, is taken from the ice itself. Since the amount of heat called as heat of solution and the latent heat of fusion are taken from the ice, the temperature of the ice reduces below the existing temperature, that is the initial temperature before the salt was added to the ice. If we go on adding the salt, more and more salt keeps on dissolving into the water, and in every stage the temperature reduces further. The process keeps on happening till the solution becomes saturated. By that we mean that no further salt can be dissolved. At this stage, the temperature cannot reduce further. So, every salt, depending upon its properties and ability to dissolve into water, has a predefined lowest possible temperature that can be achieved. This lowest value of temperature is called as eutectic temperature. There are various values of eutectic temperatures Tc for different types of common salts used. For example, KCl has a eutectic temperature of 11.1 degrees Celsius. The table salt NaCl has a eutectic temperature of 21 degrees Celsius, and so on. KOH has a very low eutectic temperature of minus 65 degrees Celsius. So adding of salt or an acid, and by using its property of getting dissolved into the water, was used traditionally for many years before the advancement of technology to achieve such low temperatures. Now another technique which should be discussed is the adiabatic expansion process. By adiabatic we mean that no heat is allowed to leave the system, neither it can flow into the system. The change in heat of the system is zero, or the heat of the system is constant. And if such a substance is allowed to expand suddenly, the heat required for this expansion is taken from the substance itself, and as a result the temperature falls down. Now this qualitative discussion can also be proved with the help of equations. We know that for an adiabatic process, PV raised to gamma is a constant, where gamma is the well-known ratio of Cp upon Cv. But for an ideal gas, we know that PV is RT, of course, for 1 mole of a gas. So this means that V is just RT upon P. If we use this here, what we get is T into P raised to 1 minus gamma upon gamma is equal to constant. So if there is a gas with initial pressure P1 and initial temperature T1, and if it expands, by expansion we mean that the pressure is going to reduce. So it reaches some value P2 and T2. Of course, note that P2 is less than P1 since it is an expansion. We must have T1 P1 raised to 1 minus gamma by gamma is equal to T2 P2 raised to 1 minus gamma by gamma. So this gives an expression for the final temperature T2 as T1 times P1 by P2 raised to 1 minus gamma by gamma. So this is an expression which can give us a value of the reduction of the reduced temperature T2 if we know the initial and final pressure values. Just for an example, suppose we have carbon dioxide gas. The initial pressure is very high, so it is compressed to very high pressure values, and suppose it is at room temperature. So T1 is 27 degrees Celsius, or adding 273 we get 300 Kelvin. Gamma for carbon dioxide is safely taken as 1.3, and this is fixed for CO2. So T2 would be just T1 times, that is 300 times P1 by P2. Now suppose the carbon dioxide is allowed to expand to a value of atmospheric pressure, that is 1 atm. So we have 1 by 150 raised to 1 minus 1.3 divided by 1.3. So just a minute, sorry, there is a slight correction here. Actually we have P1 by P2, so we have 150 by 1. Okay, so that is 300 times 150 raised to 0.3 by 1.3. And this can be calculated, and we get a result which is 94 Kelvin, roughly 94 Kelvin. Now 94 Kelvin is 94 minus 273, that is minus 179 degrees Celsius. Now we can just see how low this temperature is that can be achieved using the simple technique of adiabatic expansion. But we should note that for this high temperature drop to take place, we must be able to compress the gas initially to very high pressure values, and that is a very difficult task to achieve. But of course it also gives us very improved or beautiful results as compared to the previous case of method of freezing mixtures. There is another technique which is very commonly used in the case of traditional old age refrigerators, which is cooling by the method of evaporation under reduced pressure. Now we know that though a gas or a substance is present in liquid state at atmospheric pressure. If we reduce this pressure, the gas or the not the gas, the substance starts to evaporate. So reduction in pressure can cause evaporation in certain special substances. Now such substances can be used to achieve cooling by the method of evaporation under reduced pressure. For that, we need a compressor, say G, which can suck the substance which has got this property of evaporation under reduced pressure, which is filled inside this tube. Now since this substance is going to give us a drop in temperature, this substance is also sometimes called as a coolant gas. Now this is the region which is to be cooled. So let us call it as storage, since it is potentially to be used as a refrigerator to store something. And this region is called as evaporator. Note that since this is an evaporator, the coolant inside this tube is at low pressure, since it is in evaporator state. Now this compressor sucks this gas in and passes it to the region of high pressure. So again there is a coil like arrangement, and here we have a continuous flow of water going on. Of course this need not always be there, but it has to be there to make the process more efficient. This region is hence called as condenser. Now note that in this region the coolant is in gaseous state. When the compressor sucks it and transfers it to the other region of high pressure, due to high pressure and this condenser used, the gas gets converted into liquid state. Then it is transferred to a regulator and a valve, which regulates the pressure and transfers the coolant back into the region of low pressure, where it is then converted into vapor again. So in this process, every time the compressor piston goes up, it sucks the gas, and when it goes down, it transfers the gas to the condenser region. During each of such cycle, a very small fraction of heat is transferred from the storage region to the condenser region. So there is a net transfer of heat during each such up and down cycle of the piston of the compressor, which extracts some heat from this region and transfers it to the other region. And if this cycle is repeated for a definite interval of time, for a long enough interval of time, this region can be seen to fall seen to have a fall in temperature which is of significant value. So this is how a vapor compression machine works, and that is nothing but the refrigerator, a traditional old age refrigerator works. The typical gases which can be used in this process as a coolant are SO2, CO2, and the very famous freon gas. Of course, this has been banned, being a CFC gas, of course, because it causes harm to the ozone layer. But still, we must be aware that such type of machines were used for years to achieve low temperatures. Thank you.